Is it going? All right.
Yeah.
Cool. So last week we kind of ended off on GPIOs and sort of an intro to embedded. Does anyone have any questions from what we covered? A quick summary is sort of like the different types of processors. We have like a microcontroller, you have a microprocessor, you have a system on a chip, and they're all basically different tools for different times, right? You want to use microcontroller when you have a very fast, lightweight system where you have a very specific task. Microprocessor is more powerful and more general. That's where you're going to run an operating system like Windows, and you're going to actually have software developers develop applications like Chrome and Altium and OneNote on top of that. And then a system on a chip is kind of the best of both worlds, where it's powerful enough to run an operating system, but um, it's still small enough and low power that you can put it in your phone or a tablet or things like that. We covered briefly binary, digital versus analog, and then we started with inputs for GPIOs. So GPIO, as it says in the top here, is a general purpose input or output pin. You can see a couple of examples here of common boards that people use. So this is a Raspberry Pi, and I'm not going to write the whole thing out, but some people call it an R Pi or just a Pi. Over here on the right is an Arduino, so you can kind of read here. Uno is just one of the types. And it's important to note here that this whole thing is not the microcontroller. Microcontroller is just our friend here, right? Just this chip is the microcontroller. The part around it and everything else is the circuit board that's designed around the microcontroller. Sometimes it's called an expansion board, a breakout board, and very often for embedded, we call these development kits, right? So you don't have to, as the embedded engineer, you're not going to have to go and design all of these electronics around your microcontroller just to program it. You get this development kit and you can just plug it into your laptop, right? Same thing on the other side. There's a bunch of USB ports you can use to just immediately work on the embedded side. And on the Raspberry Pi, this is actually an SoC. So that's why you see an operating system like Linux often running on a Raspberry Pi. It's because it has a more powerful brain. Um, Obviously, it has its advantages and disadvantages. For example, it's a lot harder to do things in real time because of your operating system. It may be doing things in the background you don't know about, compared to a microcontroller where usually you have a lot of control over exactly what it's doing. But there are definitely ways to get around it, and people have built libraries to run real-time things on Linux. It's just not as reliable. So, first rant aside, we'll have many today. Planned rants, which is maybe not a rant, but it's good. So, GPIO, general purpose input output. Some microcontrollers omit the P. For example, the TMS 570, just to save brain power, they just call it GIO, but it's the same thing. General input output. And we started with inputs, yeah? So the inputs. Yes, Zinglu. So the GIO is general input output for the TMS 570, which is our microcontroller. Most places around the world you're going to see the P, but again, it's just nomenclature. So for the input, we are reading from the world, right? The input is where we get to actually understand what's happening around us. So this is my microcontroller, and this is just a little chip, right? This is a little piece of silicon that has the processor inside the brain, and runs all the code, and it interfaces with the real world through these little pins. And so with an input, I'm able to read data from the world. And this is really great, especially in the sense that the GPIO input is a digital input, and it reads a binary 0 or 1. So GPIO is a great tool for checking the status of things, right? Are you okay or not okay? Are you running or not running? Is there a fault? Is there no fault? And so you'll often see chips that you're working with. So if I'm working with, for example, a motor controller chip, right? So this let's say it's called a DR, like a driver. Many of you who have made electric longboards may find this familiar. This is the motor controller chip, or integrated circuit that's used on the VESC, which is a little motor controller to run your electric longboard motor. This chip has a GPIO output, so a digital output that is an alarm, right? And if I have my microcontroller and I'm writing code, I write my code, and if I take this and wire it to my input pin, then I can read and understand if there is an alarm from my motor controller, right? And what that tells me is that if I'm in my code, everything's fine. If all of a sudden my pin tells me, hey, you've changed state, now there's an alarm on your input, then I can know to shut down the system, stop spinning motors, and stop drawing current from the battery. So GPIOs are a great tool for sort of the state checking, right? Where you're seeing, is something on or off? Is something good or bad? Is something on fire or not on fire? And in our car, we have a lot of these spread out throughout the vehicle, right? So specific to Team Phantom, we're checking things like IMD fault outputs, right? BSPD, BMS. All of these have a fault output that we're sending as inputs to our microcontroller. So we're checking. To ensure redundancy or super safe system, as mandated by the rules, all of these GPIOs also go to some hardware system, which we call the shutdown circuit. Shutdown circuit. So in hardware, we're making sure that all these signals are not faulting, and in firmware, we're checking them as well. So we have this double redundancy to make sure that in case our hardware fails, the microcontroller can take over. In case the microcontroller fails, the hardware can take over, and they both check the same states. So all of this is just using GPIO inputs. So you can create like a super safe system with one of the most basic building blocks of a microcontroller, right? And the more things you check, obviously, the more understanding you have of your system around you. It's great practice to have a lot of these signals around the car just as system level checks and system state checks. And we really like them for those sort of errors. So with the input, we mentioned one of the first few things you can do is the pull up and the pull down resistor, right? So you have pull up and pull down. You can configure your GPIO input pin to enable either of these actually inside the microcontroller. You don't always need to provide an external pull up or pull down. Now, does anyone want to remind me why we would use a pull up or pull down?
Prevent floating.
What's floating?
Sorry?
What's floating?
Floating is like the pin is like in an unknown state. It's not high or low. We're not really know. So by pull up or pull down, we assign them a no state. It's either ground or 0 or 1. So
Cool. Yeah, that's exactly right. We want to make sure that our input pin always has a defined state, right? We want it to be either a 0 or 1, and we know that it's not floating to something random. Just a reminder that the way a microcontroller interprets a 0 or 1 is based on its logic level. So if I have a 3.3 volt logic level microcontroller, a 1 would be a 3v3 into it, right? And then a 0 volts is logic 0, which is easy. Right, so one example of this, so let's say I have a signal. So my microcontroller is here. And let's say it is the ready to drive signal in the car. So ready, all right, acronyms. Ready to drive signal, right? Good luck remembering that. So for the ready to drive signal, all it is in our car is just a little toggle switch. So the driver just has a little switch that he or she can flip on the dashboard, for example. And the way it works is something like this. So if this is a wire from the microcontroller, this guy here is a little switch, and then it goes to ground, right? So this is known as an active low signal. What that means is that normally you would think of on or active as being a 1, right? If I turn the light on, it's a 1. If I turn it off, it's a 0. But you have also this thing called active low. So active low is literally just the opposite. It's where we're saying, okay, when that signal goes to 0, that means it's activated, or it's what I expect something to happen, like it's on, for example. I say active. The signal's active when it's low, or when it's at 0. And then when it's a 1, you can just say it's inactive. So this little switch here, when the driver closes that switch, and that manifests itself just as a little toggle switch on the dashboard. When he closes that switch, this path is closed, right? So this little pin is going to be connected to ground. And so it'll read a 0. So it knows that when it reads a 0, the driver flipped that switch, and we are ready to drive. So in our code, we're going to be looking for that 0 and knowing that we can't move forward in the process of turning on the car unless the driver has flipped the switch and dropped it to 0. Now this is important because the driver may not be ready. He may be half in the car. He may be not fully kitted up in his harness and set up. His helmet may not be on, or her helmet may not be on. And so we need to make sure that the driver has acknowledged that they are ready to drive the car. So usually what we'll do here is internally we'll enable a little pull-up resistor. So probably gonna have a tough time drawing this, but inside we'll enable this little pull-up. What that does for us is that whenever this switch is not switched and not closed, this pin is actually floating without the resistor. Can you see that here? I don't know why I drew like that, but if this is open, then this pin is not connected to anything anymore. It's just this wire that's floating in space. It's not connected to ground, it's not connected to VCC anywhere. It's only through this internal pull-up that pin has any connection. And so whenever we untoggle the switch, or the switch isn't fully toggled yet, the driver's not ready yet, then that pin is pulled up to 3.3. And so we'll know safely that if we're reading a 3.3 on that pin, so if we see a logic 1, then we're not ready. Not ready, right? The driver has not given us the okay yet. If we see a 0, we're good, right? We're ready to keep going with turning on the car safely in a way that we know the driver is okay with, so that we don't accidentally start turning everything on and some other fault taking over and potentially hurting the driver or damaging the vehicle, right? So what happens if, for example, we just had a really rough ride, it was super bumpy, we're pulling up to a stop now, and this wire disconnects. This one here. What happens if we lose this wire? Now, thanks to our pull-up resistor, if we lose this wire here, our pin should automatically read 3.3 volts. Because of that internal pull-up, it should automatically see a 1, regardless of if the driver is hitting the ready to drive signal or not. Your connector disconnected and we have no more input to that pin. So we have no idea what the actual state is of the ready to drive signal. We have no idea if the driver is ready to go, if they haven't even gotten in the car yet, if they're not wearing a helmet and they're completely not prepared. We have no idea what's going on. And so this internal pull-up resistor will save us, because If nothing's connected to that pin, we know it's automatically going to pull it up to 3v3, pull it up to 1, and when it's 1, we know we're not ready, right? And this could mean that everything's fine, but the driver's just not ready yet, or it could mean that we accidentally lost this connection and something's damaged in the car. And so it's really important to have this sort of default state that is an error, for example. This default state that won't allow us to proceed unless everything's connected properly, the driver's hit that button, hit that toggle switch, and we're good to go. Let's say I didn't have that pull-up resistor, right? Let's say I was like, I don't need that. I don't want to write that extra line of code. It's a waste of my time, right? I don't care anymore. I have my microcontroller, right? And then it's connected to my switch normally, so something like this, right? Now it disconnects, but I have no pull-up, right? What's the state of the pin? You don't know. You don't know what that pin is going to float to. You don't know if it's going to, due to the noise all around it, float up to 3v3. You don't know if it's going to float down to 0 volts. And so you could be tricked, right? This floating pin could accidentally rise to 3.3 volts and tell you, hey, the driver's ready to go. Let's get going here. And in reality, this is completely open. The driver's not even in the car, or something else is wrong in the system. Because we've lost this wire, we've disconnected, and we have no default state here. There's no pull-up or anything. The pin could accidentally float to 3.3. Sorry, I realized I got that backwards. The pin could accidentally float down to ground. My bad. Which is what we said was the ready to drive, right? Ground means we're active. Sorry about that. So the pin could accidentally float down to ground, and our code would assume that everything's ready to go, right? And so we never know what that pin will float to. Maybe it'll float to 3.3, which is inactive, and that's fine for us. So putting that pull-up resistor will give us that default state where in case something gets disconnected or we don't actually have access to the real state of the system, we're not accidentally floating to the wrong state, right? If we accidentally float to 0 volts because we're an active low system, our code will interpret that as an A-OK, saying we're active, let's start this car. But for all we know, the car's on fire, everything got disconnected. And obviously you're going to be checking other signals in the system. This is just an example of why a pull-up is really important in a GPIO input. And so if your signal is the opposite, right? If your signal is not active low, let's say it's active high, right? An active high would mean that 1 is active, right? Which is kind of what you usually expect. And 0 is inactive. Right, so this is active high. If you have this, then you can imagine you're probably going to want to pull down, right, instead of a pull up, so that your default state pulls you down to the inactive, right, instead of your default state being active. So based on what you want your default behavior to be in case something unplugs or in case it's not connected, you can decide for your own system what you'd want your pull up or pull down to be. And this is like a super useful feature that we use all the time. We use it on our ready to drive signal, for example. And a lot of GPIO signals, you'll see this, especially if you're working with a certain external chip that may have some alarm outputs or fault outputs. Usually they'll tell you in the datasheet you need to use a pull up or pull down resistor. And sometimes you want to, sometimes you don't trust your software configuration, right? Sometimes you never know if it's going to freak out due to the environment, if it's going to be too hot. If, for example, if you're going into space and you have a lot of radiation, that can flip bits inside your silicon, and you don't know what impact that'll have on your code. And so a lot of people sometimes just put an external resistor just to be safe as well, right? So you have your internal one configured. Okay, this drawing's messy. Let's go to this one. So if you have your internal one configured, right, that's great, but sometimes people also just put one on the outside as well, in the actual hardware on your circuit board. And common values are 10K, 10 kilo ohms, right? And that just adds an extra layer of redundancy just in case something goes wrong in your software. So this is a really common practice. Now, how do you even enable a GPIO? It's just done in software. You enable it usually with a line or two of code. And I think Mahmoud is going to go over some of the details for how to do it. For our microcontroller, the TMS570, I'll just show you really briefly kind of what it looks like. So because we are beginners, we have this great GUI, right? This great little software that allows us to enable almost every part of the microcontroller we want in graphical format. So to enable these peripherals like GPIOs and communications, we can just click buttons and mess around. So GIO, general input output, again, the P is dropped in this case, but not in all cases. So you can look here. Remember, the very first thing you do is enable if it's an input or output, right? So if I click this button, I enable this pin to be an output. You can kind of see it with this little kind of triangle shaped guy. If I disable it, it's an input, right? It'll just come through here. And right here, you can see the pull up or pull down. So it kind of even looks like a little resistor. But just with one click, I can configure exactly what I want. Clearly not a pull up. Okay, there you go. And so it's super easy for our microcontroller in this case. In other ones, it's not that much harder. All you do usually is just one line that enables a pull up or pull down. Any questions on this so far? I'd love a couple questions. Yeah, you got one, Andre?
Oh, sure. When it comes to pulling up, pulling down, I guess this is more of active low stuff. Isn't there pins inside the the chip itself that is automatically active high or active low? Like there's pull down resistors inside the chip, not the PCB.
Yes, that's exactly right. So you can decide if you want it to be a pull up or a pull down within the microcontroller chip itself here, right?
Oh, you
So
can decide that. You don't put like a physical resistor there.
exactly, yeah. You can put
Oh,
the physical one just in case outside. This guy here, right? But you can choose in the code to enable a pull up or pull down within the chip itself.
If you go into Halcogen, you could see the pull up and pull down.
Yeah, so everything here is within the chip of the microcontroller. And you can choose on every pin if you want to pull up or pull down, which is really useful. Thank you, ... for your question in the chat. Just that one, or not just that one, but we're only referring to that one signal when we're saying that signal is active low. It doesn't mean the whole car is, just means that particular signal is with respect to how the microcontroller interprets it. It means that when it's grounded or sending a 0, that it's an active signal, right? And when it's not grounded, then it's inactive. There are a few other signals that work like this in the car, but it's pretty specific to each one. Thanks for the question, Raphael. If the internal resistor is a pull-up, what happens if you make the mistake of putting external pull-down? That's an interesting question. So essentially what you're creating is a voltage divider if you do that. I like that question. So you're going to have a fun time if you do that by accident, but let's explore. So okay, this is my pin, and I have an internal pull-up, right? And it's usually pulled up to the logic level of the chip, right? So let's say our logic level is 3.3 volts, and this is our microcontroller, this little box. That's the little chip. Now outside, you put a pull-down resistor, right? Do a better job here. Now outside, you put a pull-down, right? And for the sake of argument, let's say this is 10K, even though usually it's a little higher internally. And let's say you made this 10K. Now, what you're doing here is you're kind of demanding two things from your system at the same time. You're pulling it up and pulling it down. And so you're putting it in a defined state for sure, but the only problem is you're putting it into a state that it can never change out of, right? So what you've actually done here is you've created a voltage divider. So if you do that math, the voltage here is going to be 10 kilo ohms divided by, so the voltage across here is going to be 10 kilo ohms divided by the total resistance. Multiplied by the total voltage here, which is essentially the input voltage. And so this is going to sit at exactly 0.5, right? 10 divided by 20, 0.5 times 3v3. And that's some kind of math that I can't do. What would that be? 1.65, is that right? So if you kind of put both on your system, this line is going to stay at 1.65 volts, right? And you're going to have a tough time reading anything. So the way to debug that is by trying out different inputs, right? So if this is all connected to my switch, and you keep it open, right? Let's say it's open. Your microcontroller is probably not going to read anything real because 1.65 is not close enough to 3.3 to be a 1, and it's not close enough to 0 to be a legit 0. So it may jump around a lot and oscillate between 1 and 0. It may just pick a 0 or just pick a 1 and stay there. And then when you actually do close this, you may even cause damage to some of your components because you're essentially shorting out this resistor to ground. So it's definitely recoverable because all you have to do in software is just fix this. Or if you have access to the hardware, you can just unsolder this, but it's not going to help you if you have both by accident, for sure.
I have a quick question.
Yeah, please.
Is there ever a reason you're not going to want to pull down or pull up your GPIO pen?
On the input? That's a good question. I don't know. I haven't had, because like what you're doing there is you're letting it float into some state, right? So it's either going to pick a 1 or a 0. And I've never had a situation where I don't care where it floats to, right? Usually I want it to be in some defined state. If you can think of something or find something where you'd want it to just be random, maybe like you're making a random number generator with an input pin. But yeah, especially in safety critical systems, you really want to be sure that your pin is in a state that you're confident is real. Or is the other. But if you can prove me wrong and find some real application online, that'd be cool to see for sure.
Cool.
Challenge accepted. All right. Pull up, pull down. Same idea. Everyone good? Can we move on? I need 80% confirmation to move forward with this motion.
We're good.
All right. I have one. Okay. 1 is basically 80%. So
it moves on anyway.
It moves. Okay, I got a few more in the chat. Great. Last chance questions. I like questions. By the way, ask as many questions as you can or want. If there's no dumb question, the only dumb question, there's only like a few dumb questions, kid. There's no not there are dumb questions. Probably like a dumb question I'd say is maybe like if you ask, "Am I getting paid for this?" It's probably a dumb question. No, you're not. If you ask like, "Is there a test at the end?" Again, there's no test. But anything to do with technical questions, nothing's dumb, right? If you ask me what a resistor is, that's great. Like I love talking about resistors, and it makes me feel great if I can answer an easy question because I don't have to think, and I can just feel good about sounding smart about a resistor. So if it's an easy question, ask it. Don't keep going. Don't keep going forward, having these gaps in your knowledge because in the end, it doesn't help you and it doesn't help the team. So more questions, whatever. Cool.
I have a question then.
Please, yeah.
How much current is flowing through these like GPIOs and all that?
Yeah, that's a great question. So for example, if we did a little drawing, so if we had a 10K UV3, usually it's very low, right? That's the short answer. Usually because your microcontroller pins can't handle a lot of current. In general, the smaller your system is, the less current it can take. Current is just heat, right? So if I have more space for that heat to flow, then I can take more heat, I can take more current. And that's why people use things like heat sinks. So they'll put like a big block of metal on something, right? And that allows more heat to dissipate, and we can get more current and more power with that heat dissipation. But in the case of a GPIO, it's usually very, very little. So usually a microcontroller will specify something like 10 milliamps on the pin. If you just have a pull-up resistor, let's say this closes, right? So I have now current flowing in this path. So classic V equals IR. Now, how do I do current? Move things around. I equals V over R. If anyone has questions on this, please ask. And I'm sure I'll make many mistakes, so please call me out as well. 3V3 divided by 10K. Right, so that's going to be something like 0.33 milliamps, right? Someone wants to double check that, that'd be great. A good little rule of thumb is if you're dividing by a kilo ohm and you just have a normal voltage, you're probably going to end up with milliamps, which is a good rule, but very small, right? Look at this, 0.33 milliamps. That's 0. A bunch of zeros, 33 amps. So we're talking very low currents, which is good. Low heat. We're not overstressing the processor. We're not requiring a lot of extra cooling, right? You'll notice even the more code you run on your microcontroller, the more peripherals you're using, the more pins you're using, the more current you're going to be dealing with. And so that's when you see processors start to heat up. Good example is on like a desktop PC, right? A lot of them, especially gaming PCs, there's a lot of cooling that's going on in there to render all those graphics with your GPUs. So the more current you have, the more cooling you need. And for our little pull-ups, very little. Thanks for the question, John. Right. GPIO outputs, again, interrupt whenever. GPIO output. It's a very hard to read color. So you can imagine you're taking signals in, reading things. You also want to affect the outside world, right? And that can be done with the same pin, but configured as an output. And usually you can't do these at the same time. You're either an input or you're an output. You're not going to be both at the same time. Although there are very few exceptions. There are a couple instances where you're switching between them, but we can get to those later. I just want to go on another rant here. Let's say I didn't have this resistor. I'm going to bring this up real quick. I just had 3V3, right? No resistor, just a wire, and then a switch, right? Well, when I close this switch, essentially what I'm doing is the exact same system as before. So I can do the same kind of math to figure out what current is flowing. So V equals IR. I equals V over R. But what's our R in this case? Someone tell me.
Basically 0.
Yeah, right. This is going down to 0. 0 is right. If we just have a wire inside of our resistance, remember a resistor resists flow of current, right? It's adding something to block that flow. So if I get rid of it, I've basically opened up that flow of current enormously, you know, and that resistance is only the resistance left in the wire, which is almost negligible. And so if I just do this, if I connect 3v3 straight through no resistance to ground, my current becomes infinite, right? With that really low resistance, and this is what's known as a short circuit, right? This is bad because you're drawing an infinite amount of current from your power supply, which obviously, I don't know any power supply that can do infinite current. If you do, let me know, but that's going to damage your circuitry. It's going to damage your microcontroller, and no one's going to have a fun time this way, right? So all a short circuit means is that a short is two things are connected. I can short two pins, which means I'm connecting two pins. I can short power to ground, which is the most common use of the phrase a short circuit. And that's usually when you blow up things or when you damage your circuitry. So you always need to be careful not to do this. And turns out it's actually pretty common by accident, especially if you're messing around in embedded and you have wires everywhere. You can accidentally connect these together, especially with your GPIOs. So just be careful there. Okay, GPIO output, no big deal. Same kind of idea, right? If I'm in my handy dandy GUI, I click one button and now I'm an output, right? It's not revolutionary in terms of different from what we talked about before. So the GPIO output, again, 0 or 1, right? And as you've heard me say thousands of times before, depending on the logic level, it manifests itself in different voltages, right? 3v3 if it's a 3v3 volt logic level, 5 volts if it's a 5 volt logic level, and that's specific to each microcontroller, right? So the GPIO, you have a couple different options in terms of how you want to use your output. So they're called push-pull and open drain. Weird names. Kind of makes sense once you hear about it, but initially it took me a while to really understand what they meant. But the concept is simple. It's very similar to how we talked about a floating pin before. A push-pull output. So if I have a microcontroller, right, this is the chip. This is my pin, and I've made it an output. This is my shorthand for output, O/P. So I made an output. Push-pull means that I can define the output to be 0, or I can define it to be 1, which means it's actually going to be measuring 0 volts or 3.3 volts. And so you can think about it essentially as pushing your pin up to 3.3 or up to your logic level and pulling it down to 0 volts. So you can do one or the other. You can push it up or you can pull it down. And you have exact control over how your output behaves. And this is usually the default way we use GPIOs. We're usually pretty careful about wanting our state to be defined, right? So we can push it up to 1 or can pull it down to 0. That's what a push-pull means. Open drain. Not as commonly used, but definitely is used in the field. So microcontroller, right? Pin. Open drain means that I can go down to 0, but I can't go up. There's no pushing up to 3.3 volts. There's no pushing up to my logic level. I'm essentially leaving that top state undefined. So I can pull down to 0 volts, or I can let the pin float, which seems counterintuitive, right? We were talking about making sure our pin is defined in every sort of state, especially for inputs, reading signals, and for outputs, we want it to be defined as well. Open drain is kind of a weird state, right? And it's useful in a couple of different scenarios. It's pretty rare that we want to leave it floating. So often what we do is enable a pull-up, right? And we can do that internally if we want, or we can do it externally. It's up to us. But what that does is when you pull it to ground, it's 0. When you leave it floating, it's pulled up to 3.3, right? So you're essentially creating that logic 1 state on your own with the resistor. And where this is useful is when multiple players, multiple microcontrollers, multiple chips, multiple sensors want to have control over the same line. So it's basically a way of sharing. If you think about it, if I have control over my line, right? Let's say that's a signal. I'm outputting a signal that is a fault state, right? I'm saying this is a fault state. I'm gonna, let's say I just had push-pull, right? I want to define it as 5 volts. Everything is good. Or sorry, 5 volts or 3.3 volts. Everything is good. My logic 1, that's fine. Or 0 volts. Everything's bad. Sound the alarms. Everything's on fire. But let's say I want multiple people to have access to that line, since that is the line that's going to alert the whole car, for example. So I can say, let's say microcontroller 1, Tim, right? Tim is controlling this line. Microcontroller 2, Alice is another microcontroller. She's also wanting to control this line, and whoever else you want, right? Now this line is the holy grail of lines. This is the main alarm that's going to alert everyone that the building's on fire, that the cars stopped working, that something has gone wrong, right? And what did we say? We said 5, right? 5 volts. 5 volts is okay. And 0 volts. Actually, let's stick with our 3.3 because I think that's more common. VV3 is okay. And if we see 0 volts on that line, okay, something has gone wrong, right? Bad. The alarm should sound, for example. Now, what if Tim sends a 3.3 and Alice sends a 0? Like, they disagree. Alice thinks that there's a huge problem, but Tim is like, I don't think so. Everything's fine to me. Well, all of a sudden, you have a 3.3 volt on that line and a 0 volts on that same line. Now, does that look familiar? That's essentially what we had in our short circuit. We had 3.3 directly connected to ground, right? And that's a problem. If they ever disagree, if Tim and Alice ever disagree, we're going to have a short. And so where we thought we made a super safe system, in the sense that we had 2 people checking, 2 people could alert the system that there's a fault, now all of a sudden we've created a short. And everything catches fire, and our safety system accidentally killed everyone. No bueno, right? And so people invented open drain. And what open drain allows you to do is rely on your pull-up resistors. So let's approximate each of our microcontrollers as just a switch for now. Right. And so that's, I guess this is Tim, right? Tim's here. Let's put Alice here for the time being. So she also has the capability to pull this down to ground if she sees a fault. And then let's say this goes to our alarm, right? So let's say we have a pull-up resistor. If we're using each of our pins in open drain mode, right? So let's say this is open drain, right? I only have the capability to pull it down. I can either pull it down or let go completely and let it float. Same here. I can only pull it down. What that means is that we're not going to have that accidental short anymore. We're not going to have the situation where Tim forces this to 3v3 and Alice is forcing it down to 0 volts, right? Neither of them have the capability to do this anymore. So if any of them see a fault, they can both, or just one, if only one sees a fault, they can both close their switches. For example, this is done in code, of course. This switch is just an illustration, but your GPIO would output a 0 volts at that signal. They can both switch it to ground if they want. Or only one of them can switch and the other can let it float, right? Because Tim lets his signal float, if Alice were not here, it would just be pulled up to 3.3 volts, right? And that's fine. But because Alice is here and Alice sees the real problem, right? Her microcontroller knows that there actually is a fault in the system and this line should be at 0 volts. Tim's floating pin will not affect the system anymore. Alice will take precedent and her 0 volts will sound the alarm. And so because they both use their microcontrollers in open drain scenario for their GPIO output, they're able to collaborate on the same line and have a safe way of both of them alerting the system of a problem. Whereas with our push-pull, we had the problem where they were fighting for that line. They said, I need to define it as 3v3 or 0, and I need to do the same thing. And so when they disagree, we have the potential of causing a short in the system and damaging everything. But with open drain, we can play nice, right? We can have multiple microcontrollers, multiple sensors, multiple signals, multiple switches, work on that same line in a safe way and in a redundant way, in the sense that if Tim fails, if his microcontroller completely dies, we still have Alice controlling the line, and vice versa, right? And so open drain allows you some really great capabilities of redundancy on that same signal. And this is something we do even on the VCU. So on the VCU, this alarm, let me draw a new one maybe. On the VCU, it's a little different in the sense that our alarm that line is actually the reset line of the TMS 570. If something goes wrong outside the car, we want to be able to reset it and reboot all the code, right? And the things that are working on that line in tandem, one is just a little button, right? So the user itself can see something going wrong. Maybe Zinglu is working on the VCU. He can kind of feel with his hand that the microcontroller is getting really hot. Something's not going well. First thing he tries is a reset, right? This little button that pulls it down. And the other thing is a little guy called a watchdog. And we'll talk about this in another lesson, what this means, but you can essentially think of it as a little pet that's helping you out, right? Watchdog. This little pet is checking around the system, looking everywhere, and if something goes wrong, he's gonna send a 0 to this line. Otherwise, he's open drain. right? So these two things can work in tandem. Pull up resistor, of course, to make sure that if they need to, they can reset the TMS 570, but they're never going to cause a short, and they're never going to break the system while trying to save it. And so open drain has its places, definitely used in a lot of applications, and super useful when you want this capability of this guy or this guy or this girl or this sensor or any of these systems working on the same line and all having that redundant capability of making sure you're safe, right? That's a great application. In a lot of other applications, we want that defined state, right? Where we want to know, is my LED on or off as an output, for example? Or I want it to be a push-pull, right? I want it to be 3.3 volts or 0 volts, and nothing floating, nothing in between. And those are sort of the two major states that your GPIO output can be. Questions?
So when you're doing this redundant shared line alarm or whatever, all systems on that line have to be open drain?
That's right. If you have one that's push-pull, then if it thinks that it should be a 3.3 volts and it sends a 3.3 volts, if everyone else doesn't think that, if everyone else disagrees and says it should be 0, you're going to have a short problem where that same line is going to be forced to 3.3 to connect 3.3 and 0 volts together, and something's going to get damaged in there.
What if you do push pull and open drain at the same time? Is that possible?
On the microcontroller?
Yeah, because I think I've seen, like on STM32, there was a mode where it can do both at the same time.
I don't know. It's possible. I have never seen that personally, and I don't know why you or what that would even look like what it means. Are you undefined or defined? But that is maybe a thing. If you find a good resource or something that shows how to use it or when to use it, that'd be cool to show the team for sure.
Yeah.
On the TMS 570, if you guys want to look again, this is a little Argui, right? Can anyone spot it? All right, open drain. So if I click it, now I have an open drain output. If I don't click it, push pull, right? You can kind of see this little diagram. The little top bit disappears, so I can't pull up anymore. You see that?
So it's automatically push pull.
Automatically push pull, which is usually what we do, but I click open drain and now I can't go up anymore. That little top bit disappears. So for us, it's really easy. In any other microcontroller, if there's no GUI like this, again, a couple lines of code in your configuration at the start, and it's not too bad. More questions?
In the TMS
yeah.
570, oh, sorry.
Please, yeah.
In the TMS 570, you connected all that into the reset button, right?
That's right.
Reset pin. Do you have to set the reset pin as active low?
That's a great question. That's essentially what it is. That's a really good question.
It's always active low.
This is the one that we actually don't have control over this in the TMS 570. This is predefined within the chip. The reset pin is active low. Great question. I think we have that question again by ... famous in the chat as well. That's exactly right. Active low is what this reset pin is. And you can, if you're looking in a schematic or a data sheet, the way they often show that a signal is active low is in the name. So like if I look at in the data sheet, right? Data sheet. Woo! Double E of the microcontroller. It's going to be like all the pins and then like pin 19. Reset underscore N. This N part is what gives it away. This is what tells you it's almost like negated or opposite, right? Or not, right? So it's an active low signal instead of what you would normally expect. Sometimes you also see the little hash symbol instead of the N. Same thing. And then I think the last one is with a bar on top. These are all equivalent ways of showing that a signal is active low. And so if you're ever drawing a schematic or referencing a data sheet or talking about an active low signal to someone, typing it out in this way is the most clear to make sure you're indicating what they should expect, right? You say like, oh, the reset pin went high. It's like, okay, so it reset the microcontroller. Well, no, because the reset pin is active low, right? Which you would have known if you had written this down. And what that means is that when the reset pin is low, it's active. It's active in what it needs to do, which is reset the microcontroller. So when that pin goes low, as we know from any of these, then it's being reset. Whenever that pin is high, we're chilling, everyone's fine, and there's no need to reset anything. More questions? Thank you for that one.
Okay, I guess more on the reset pin. So
Yeah.
what does it do? It just turns everything off and then turns it back on again. That's literally what it does.
Again, really good question. There's actually 2 reset pins on the TMS570. Right, so if I remember right, there's a... Oh, actually, I forgot. You can actually put a lowercase n before as well. That also does it. This is actually what they do in our data sheet. So I'm not going to write it all out, but this PORRRST is power on reset. So, yeah, damn it, I'm going to write it. Power on reset. Oh, good. Reset. And the RST is just the normal reset. And the difference between them, this one actually power cycles the whole chip. It's going to reset power for the whole chip and start everything again. So the code will begin again, but you'll have a full power cycle of all the peripherals inside your microcontroller. So anything drawing power, GPIOs, clocks, peripherals, communication protocols, all those powers are going to be reset. And usually you have a lot of different rails internally. For N reset, all that happens is code restarts, right? You don't get this power reset, power cycle that you do with the NPORRST. So in both cases, your code is going to restart, but in the power on reset, you're actually going to cycle power through everything inside the microcontroller. And sometimes, and actually on the VCU, what we labeled it on the circuit board is a hard reset and a soft reset. Right, so we called this one hard reset, and we called this one soft reset. The difference just being in that power cycle. Does that make sense?
Yeah, thank you.
Cool. Any more questions? All right, one last rant and then we'll be done for today. So we talked a lot about inputs and outputs for the GPIOs. A great way to interact with the world. They're actually pretty similar in terms of how they work inside. So we do a little zoom in. So let's say this is my microcontroller, right? Same drawing as always, it's just massive now. There's the pins on the outside, pins, pins, pins. Here's the pin I'm working on. Right, I'll just draw it big. So this pin's coming in. And let's say we are an input right now. Actually, let's start with output. Output's a little easier to explain, I think. So we're from this side. So this is a output, right? Output, so I'm sending a signal out of the microcontroller, right? I'm defining it to be a 0 or a 1, let's say in push-pull. So the way that happens, pretty interesting. Essentially, it's based off of something you'll learn in next week's electrical lesson about transistors. And you don't have to think about them too hard right now, but the idea is something like this. So if you take a look here, this is what they call a transistor or semiconductor. It has 3 terminals, right? You can imagine this one coming in here and then leaving, essentially being 2 terminals of a switch. And this side being the control side. So this is literally a button I could press. I could send a signal here, and that would close this switch. It would connect these 2 guys together, right? That's all that's happening here. Same thing on this side. I have a little input. I could press this button or send it a signal, and it'll close this switch. It'll connect these 2 things. So the thing we're trying to do here is use these connections, these inputs, to either connect our output pin to ground through the switch or up to 3.3 volts, which is exactly what an output does, right? That's what your push-pull will do. It'll connect it to 3.3 or to ground, right? Now, the difference between these 2 switches is that, and let's say again, my logic level is 3.3, right? That's our favorite one. The way these 2 switches differ is that if I send a 1, right? 3.3 volts is a 1. If I send a 1 here, okay, a 1 is connected down to here. This switch will close. This switch will stay open, right? They're literally opposites. If I send a 0 here, this switch will close, and this one will stay open. Got it? So it's a little backwards to what you would think, right? If I send a 0 from my processor brain, if I have a 0 here, this switch will close, and the pin will be connected to 3.3, which is a 1, right? If I send a 1, this switch will close, and my pin will be connected to ground, which is a 0, and this is not connected. So it's backwards. So what you do is you put this thing called an inverter before. And it's just a NOT gate, right? That's the same thing, a NOT gate. If it's a 1, if I put in a 1, it'll give me out a 0. If I put in a 0, it'll give me out a 1. And that's how your processor actually does the GPIO output. So it says, okay, I want a 0 on the output pin. Okay, send a 0. Inverter makes it a 1, the NOT gate. The NOT of 0 is 1, and the NOT of 1 is 0. Makes it a 1. My top guy doesn't like 1, so it won't close. My bottom guy likes the 1, so it'll close and connect my pin to 0. And like I desired from the start, I actually get a 0 on the output. If I do the opposite, if my processor wants a 1, my NOT gate will make it a 0. It'll close the top switch, and the bottom one will not close. And I'll actually get my output pin connected to 3.3 volts, which is a 1. So my processor wanted a 1 and it got a 1. And that's basically the internals of a GPIO. The reason they do this, if you look now, your pin is connected to 3.3 volts with its own little power supply, right? If I had just connected my processor straight to the output pin, I would be drawing all the current for that pin from my processor brain, right? And this guy doesn't have a lot of current to give out. And so what we're doing here is we're creating a little buffer system where we can send the signal we want and get that on the output pin, but use it with its own little independent power source, right? Or power sink. And so this is the internals of a GPIO output. Now an input, it's pretty interesting. It's almost the exact same thing. It's like this exact same thing, but rotated 180 degrees. Now I have an input, IP input, rotated 180 degrees, right? So rotate this whole thing, it would look something like this. Not gate. And take a look here. If my input is a 0, right, what happens then? It's a 0. Not gate will turn it into a 1. Now my bottom switch likes the 1s. Remember, my bottom switch will take the 1. So this is a little switch. This is also a little switch. My top gate will not close, and my bottom gate will close, right? And so this pin, which is connected to the processor, will read a 0 because with that 1, my bottom switch closed and connected that pin to 0 down to ground. And so that's how I read my processor. So if I had an input 0, my processor also reads a 0. So exactly what we want. Let's say I have an input 1, right? 1. Same story. Not is a 0. My top switch likes that 0. It will close and switch, connect these two paths. My bottom one will not close. And so that pin is connected to 3.3, and I get a 1. Remember, 3.3 is logic level for 1. And my processor sees the 1, which is exactly what we had on the input pin interfacing with the outside world. And so what's kind of weird to see is that, I wish I could zoom out better, but this whole system for the input, it's 180 degrees rotation of the output. And so you can reuse this little piece of silicon inside your chip a bunch of different times for the input and the output. And it's super useful. Any questions? This was the final rant of the day, so ask away.
What's up with the NOT gate? Doesn't it work without the NOT gate?
Yeah, good question. Yeah, no, that's definitely a good question. Let's try it. Can you walk me through it?
Sending a 1 or a 0 anyway would do the same thing either top or bottom, wouldn't it? Oh, it would flip.
Yeah. So if I sent just the 1, if I got an input as a 1, right? That would turn on my bottom switch and close it. I'd close this one. And this one would not close, right? My bottom switch likes the 1.
And inside it sends a 0. Oh, okay. The processor reads a 0.
You get a 0, right?
Gotcha.
So that's
okay.
That's
Cool.
the tricky part. If it worked without this, that'd be way better because it's less components, less cost, smaller, right? But these computer engineers developing the silicon, they needed to try it out, right? So they tried out this, Unfortunately, it's literally the opposite. So like, okay, well, how do we fix that? Well, why don't we flip it before, right? If we put this NOT gate, it's going to get us that 1 that we want. Make sense? And again, we do this because it provides a little buffer from the outside. So we can do this from our own internal power sources, and we're not directly connected to the pin, which may have a huge current source, which may get damaged somehow from external components, and it's not as safe as buffering it like we are here. Okay, that's enough of me ranting. Thanks, guys. If you have more questions, please yell at me right now. Or if you don't want to, feel free to message in the Slack, and we'll continue sometime next week.
Thanks very much.